Welcome back to this set of videos. My name is Revi and I'm a London-based private tutor and economist. In this video, I want to tell you about risk aversion and I want to give you a second definition. So in a previous video, we talked about risk aversion, not as uh, disliking of risk, but we wanted to be a bit more precise. And what we effectively said is if a person is risk averse and he's faced with a lottery and he's faced with the expected value of the lottery, he would prefer the expected value of the lottery. What is the second definition that turns out to be equivalent to that? Would be that a person is risk averse if their utility for money, that's what we've been focused on. And actually, I should add here their utility for certain money. So when we think about the utility, we're giving a utility that he would get when he get a sum of money for certain. And their utility for certain money is concave. So remember, I could pick any arbitrary point. Say this was money, X, money. This was utility of X or utility of money. I could pick any arbitrary point here and here. Okay. Note that I haven't really given you so far in the previous video the shape of the utility function. Okay, because I didn't want the shape to be important. But note this shape could be like this. So look, a concave function, right? U of X, or it could be like this, a convex function, or it could be linear for that matter. Okay, so a risk-averse individual is someone with concave utility function of sure money. And this definition is equivalent to the previous definition and this comes from the definition of what does it mean to be concave. Okay. What it means to be concave is the following. Let me take away this again. Okay. So one definition of a concave function is if there's some probability of this event, P, and there's some probability of this event, 1 minus P, okay, then here, remember the expected utility maximizer assumption. So we're going to have some utility for outcome 1, some utility for outcome 2 with this difference probability. And if you find the expected value, let's say this is the expected value here, note that it seems a bit closer to the first outcome. So probably the probability of P there would be higher than 50%, right? In the way I've drawn it. Of course, I could have drawn the expected value closer to here, and therefore this P would have been smaller than 1 minus P. But here's something that I've realized students don't immediately see. If you calculate the expected value, which is the average of these two outcomes, and you find this X value here, and if you calculate the expected utility, which will be somewhere here, okay, let's say somewhere here, expected utility. If you've done the maths correct, what must also be true is that if you connect a line between these 2 points, the coordinates of the expected utility and the expected value should be the same. So I was, probably haven't done this precisely, but it's close enough. You could see that this lines up and it's in this line. If, for example, you realize that you have this expected value here and the expected utility is up here, then you must have made a mistake in the calculations. So every time you calculate expected values or expected utilities, they will have to lie in the line connecting these two outcomes. Okay? What will happen if probability is, let's say, this P here is larger? Well, this expected value will shift to this direction. This expected utility will shift to this direction, and the coordinates of the two will shift along the lines connecting the two. Okay? And if a function is concave, what you know is that if you take any two arbitrary values, say for example, you take value x1 and x2, okay, and you take a linear combinations of those, okay, or a weighted average effectively, which is what we're doing. So I do lambda plus 1 minus lambda, where lambda is some number between 0 and 1, okay? Then that's the expected utility, right? This bit here is the expected utility. This bit here will be greater or equal to the utility of the expected value. X1 plus 1 minus lambda x2. In other words, if a function is concave, let's say, for example, I don't give you the function, what you know for sure is that if you plug in the expected value, so the lambdas, instead of the lambda, you have the p, for example, but you might see the definitions of concavity with lambda, and that's why I'm using lambda there. But I could have also used p, and perhaps maybe it would have been better if I had used p there. But here, what we're really saying, this function is concave, then it must be that the utility of getting this expected value for sure should be somewhere higher. Okay, utility of getting this for sure should be somewhere higher. Yes, so I've made a mistake here, right? So the inequality should go the other way with a little warning sign. Right? And therefore, what we have here is if I plot a concave utility function, right, I could see that this bit here is the utility of the expected value, is the utility that I would get if the expected value is for sure. Because remember, and maybe I'll write this down, this is utility of X, this is utility for sure money. Utility for sure money. And with this, I've served the purpose of this video, which is to show you a second definition, which is equivalent of what does it mean to be risk averse. I will see you on the next video.